Okay, you can hear me, perfect.
The floor is yours.
Okay, so hello everybody. My name is Patrick Pfeifel, and today I'm going to talk about the safety impact of inherent interpretability on deep neural networks for pedestrian detection. Our work closely relates to 1, AI-based pedestrian detection, and 2, safety standards for software. We choose the DNN for center and scale prediction as our baseline and starting point. It is a single-stage and anchor-free pedestrian detector and offers state-of-the-art performance on the CityPersons dataset. In terms of safety standards, we are focusing on the D0178C. It originates from software consideration for airborne systems. Regarding the DO process, we have the first step, which would be the definition of a high-level requirement for the software you would like to implement. After that, there will be the decomposition of this high-level requirement into multiple low-level requirements. After that, you should be able to directly implement source code from the given and derived low-level requirements. Finally, you need to guarantee and establish bidirectional traceability between low-level requirements, source code, and high-level requirements. In conclusion, the main concepts of a DO process are decomposition and traceability. In combination with the AI-based pedestrian detection, this leads us to our problem statement. We are currently in the situation that established safety standards like the DO cannot be applied to deep neural networks, at least directly. The first reason is that we are using a requirements-driven development process for software, which of course is in natural contrast with machine learning approaches right now. Secondly, we are facing a complex input domain in our automotive setting. We are learning from high-dimensional and unstructured data because we are using real-world data. Our proposed methodology to tackle this issue is to rethink the D0178C in the context of inherent interpretability. Our motivation can be shown in a question and answer manner. And the first question we are asking is, how can we decompose a DNN? Our answer is inherent interpretability. The first step in our methodology is that interpretability gives us a concept for the decomposition of a deep neural network. Of course, that's on a very abstract level, but if you're now focusing more deeply on the requirements, we can ask, how can we define requirements? And interpretability introduces task-dependent meaning. And if we can find and identify meaningful components in our DNN architecture, we are also able to process them by requirements analysis. The final step towards a conclusive safety argumentation is all about generating evidences. In the end, metrics should show fulfillment of the derived requirements, and that shall be done by quantifiable and requirements-based evidences in our methodology. Our understanding of inherent interpretability is largely based on the work by Cynthia Rudin and especially the publicated proto-PNET by Chen et al. We simplified their reasoning process to our reasoning process for pedestrian detection. A pedestrian is detected because its latent representation is close enough to a prototype for a pedestrian center. Here, we have two meaningful components. On the one hand, we have a latent representation. On the other hand, we have a prototype. A latent representation is a vector that represents the inner understanding of a given receptor field of an image. You can see the receptor field on the right-hand side in the image. It's the light blue area. This area will get processed by the feature extraction, and the extracted features are then stored in our latent representation, which is a vector in our latent space. We then compare the prototype, the latent representation, with our prototype based on the Euclidean distance. We then decide if the latent representation is close enough to the prototype, whether we have background or an actual pedestrian center. Prototypes are vectors that clusters those pedestrian features in our latent space. Because inherent interpretability enables the meaningful decomposition, we can now have a look at our requirements analysis. Like I mentioned before, The first step would be to define a high-level requirement. Our high-level requirement is the latent space of a deep neural network for pedestrian detection shall be interpretable. The second step is decomposition. We are deriving now 6 low-level requirements from this one high-level requirement, and we are also implementing source code. For instance, our DNN architecture in a deep learning library. What's new here is we also have DNN artifacts. A DNN artifact is for us a learnable parameter of an interpretable DNN that is explicitly formed by source code and low-level requirements. A good example, or the best example, is our prototypes. The final step is again the bidirectional traceability. We are now able to assign source code and DNN artifacts to the derived low-level requirements. This can be done by this traceability matrix. To prove our proposed methodology or concept, we also implement an interpretable DNN for pedestrian detection. Because it's largely based on the CSP and proto-peanut approach, we call it center scale and prototype prediction, CSPP. You can see on the left side, the feature extraction is kept the same as the CSP approach. We have our central latent space in green, and we are applying the detection heads of the CSP and the proto-peanut approach onto the latent space. Because of the traceability, we are now able to assign our low-level requirements to the meaningful components in our DNN architecture. That means low-level requirement 1 and 2 are explicitly targeting the latent space. We want to explicitly structure the latent space, and this is done by applying our prototypes. The third low-level requirement is focusing on the complete reasoning process. It is interpretable because it's based on distances. The fourth low-level requirement is all about the threshold for accepting or declining a detection. So we are learning here from our training data set, the statistics, whether we can decide we have background or the actual pedestrian center. The final step in our methodology is the evaluation, so generating evidences. You can see here latent representations and prototypes dimensionally reduced into the 2D space. This is done by application of PCA and TSNE. We trained 4 prototypes, which are color-coded, and we are also evaluated the confusion of each latent representation. So we can now assign the true positive, false positive, background, or false negative to latent representations. And we see the functioning of our loss formulation. We are pulling true positive to our prototype. We are clustering them around them, and we're pushing background latent representations away. Of course, we can also evaluate the true distances, or in this case, similarities. Low distances mean high similarities, and we can also see that the green box plots have a higher similarity to prototypes than the blue box plots. In the end, we also evaluated the performance in terms of log average miss rate. As our baseline CSP gives 11% log average miss rate, we implemented for fair comparison also a simplified version of the CSP, which lays for the reasonable setting around 15%. And our CSPP with 4 prototypes is able to achieve around 14%. So we are offering competitive performance with an interpretable DNN for pedestrian detection. Thank you very much for listening. If you have any questions, feel free to ask.
Yes, thank you, Patrick. Actually, there would be time for some questions.
Maybe a question regarding the number of, in the slide before, the clusters you showed. You did,
yes. Yeah.
You selected 4 prototypes. Have you also tried out others? What are the reasons that you used 4 prototypes?
That's a really good question, because it's non-trivial to determine the amount of prototypes needed for our task. We also evaluated 1 prototype you can see here. But to be honest, 4 is just an arbitrary number. We are not focusing on the performance. So 4 was a working thing for us.